Good morning, everyone. Let's start our second day. So we have a list that you have to sign every day, so we can. So that's a requirement the university makes, so we can provide you with the certificate of participation. I will be circulating this just once a day. If you are presenting poster, please make sure that your poster is in the correct place, because we are all going there after last session today, okay? All right. So it's my pleasure to introduce now Dr. Daniel Jaffe, which, what I gathered, he's working with cool stuff, mostly code, stars, star formation, regions, and everything from an infrared perspective. Is that right?
Fair enough.
Okay, thank you.
Thank you. So I know it's early still, but I hope you're going to be awake, because I'm going to actually ask you questions sometimes, so you need to be on your toes. I'm going to start today with some basic background about infrared astronomy and infrared spectrographs to give you some familiarity with the field. I think it's important even for those people who are observers, or even people who are just using space instruments where you're sending in your requests and getting the data back, to have some understanding of some of the problems we face and some of the trade-offs that we make in design and in use of instruments, so that you really understand some of the potential problems with your data and some of the reasons why instruments behave the way they do. So I'm going to give you a bit of background to give you some familiarity with that. Okay? I build things, but I don't use things. Excuse me. So how is this supposed to work that it's not working? Is it not on or something elementary like that? I don't have my glasses on. All right, perfect. Now, see, this is how it goes. Okay, so I'll start by going through what is the infrared. I mean, this may seem obvious, but it's not quite so obvious. And then talk a little bit about the instruments, requirements, and then about the instrument that we're building for the Giant Magellan Telescope with the uneuphonious name of GMTNIRS. And then a little bit about spectrograph basics, and then about some background about the key ingredient in the instrument we're building, which are the silicon immersion gratings that make the technology that really enable what we're doing. So let me just start with a little background. There's really several different ways you can think about why the infrared starts at 1 micron, which is kind of our current traditional border. And one of them has to do with the properties of silicon. So why are silicon detectors so dominant in the optical? Well, it's because of now close to 60 years of technology development, and every time somebody tries to make things out of something else, the industrial might of silicon production, both for electronics and detectors, wipes them out. And silicon has this interesting property, which is right at about 1 micron, it becomes transparent. And this will become the reason I'm mentioning this also is it'll become very important later when we talk about the immersion gratings. But because it becomes transparent, it doesn't absorb light, and therefore silicon detectors stop working. And so you'll often find a technology boundary right at a micron. So the optical will go right to just past a micron, and the infrared will start there simply because that's where you can't use silicon detectors anymore. Another important reason is the atmosphere itself. And so from the ground, the atmosphere transmits pretty well throughout the optical, but starting at just past a micron, what you'll notice is there's a series of bands where the atmosphere doesn't transmit very well. And I chose this particular slide for a reason, which is it shows a very high altitude observatory, 5,600 meters, and one at 2,600 meters. And what that does for you is where you see a big difference, that tells you what the absorber is. So which absorber makes the difference between these two slides? Water, right, exactly. So when it's kind of interesting because it shows you that at very high altitude, you get this almost continuous ability to observe out to about 2.5 microns. And also you get to work out in the 20 micron range. And the GMT is comparable to this, and you'll notice that this is a reason why we're not pushing very hard out in the long wavelength infrared, because there's just not much transmission. So what we have is a series of windows, and these windows are defined for us by the atmosphere. So the J window is here, the H window is here, K here, L here, and M here. And that's just because that's what the atmosphere gives us. So another thing that determines how we classify what different parts of the infrared is by the background. So the background that we cannot avoid is the background that comes from the emission by the Earth's atmosphere and the telescope. Because they're all warm, they're radiating at infrared wavelengths, and while that radiation is peaking at 10 microns, there's a strong and significant tail that goes into the near infrared. So when you look at this, this is our actual calculation of the background that we get in electrons per second per pixel at the detector inside of the GMTNIRS instrument as a function of the band. And you'll see that at J and H, it's vanishingly small. By the time you get into the K-band, particularly in the long wavelength end of the K-band, this number is somewhat larger than the dark current from the best detectors today. So it's already becoming a factor in our noise calculations. By the time you get to the L and M bands at 3.5 microns and at 4.5 microns, the number of electrons per second per pixel are becoming quite significant. So they're dominating the noise out here, and that makes a very big difference. So we make a strong distinction then between not only the optical and the infrared, but between the J, H, and K, where the background's not terribly important, and L and M, where the background's quite significant. And it's a very discontinuous jump there because you're on the Wien side of the black body curve. So if you want to calculate your background, you can. Here's your relationship here, where you take the black body emission and the bandwidth covered by your spectrograph on a given pixel, the area of the telescope, the solid angle of the pixel in the sky, and the emissivity of all the stuff outside of your system. And then you just divide by the photon energy and you get the counts. And then, of course, you have to propagate through your instrument to get to electrons. That's not the only background we have. In the near-infrared, we also have significant background from OH night sky lines, particularly in the J and H bands and in the lower part of the K band. This is a raw spectrum of the H band taken with our instrument IGRINs. So this is the entire H band from 1.4 to 1.8 microns. It's a cross-dispersed instrument, so you're seeing different orders here. And many people over the years have had this dream of building an instrument that filters out these lines because the thermal background, as you saw in the last slide, is very, very small. And if you could just get these lines out of the spectrum, you'd have extremely low noise in this interval. But what you see when you blow up a part of this band, do you think the other one works any better? Let's see if this one seems to work a little better. Yeah, when you doesn't want to. Yeah. When you blow up a part of the band here, you see that in between these bright lines, there are many faint lines, and there are literally thousands of lines, and even these fainter ones emit a significant amount of radiation. So typically, you can subtract the signal by switching back and forth along the slit and taking the difference between two measurements with your object in two different places. But even when you do that, the noise from these lines, the uncertainty that's generated by them remains. So they're a significant factor at the places where they are. And this is one of the advantages of high resolution is there are some significant blank spaces, and if you're at low resolution, you're smearing the lines out over them, and they're adding to the noise everywhere. So there are some places where you have extremely low noise in the H band. because of the fact that there's no thermal background, and you can get in between these lines in some places. So another issue is the materials. So this slide is not precise. This is from an optics manufacturer whose criteria are somewhat different than ours. But the one thing I want you to notice is that normal glasses that we tend to use very frequently in optical instruments, because they're inexpensive and easily obtained, stop transmitting at around 2 microns. And so as a result, you can't build infrared instruments that use these glasses. There are a lot of other materials that have various ranges over which they're usable, and as a result, as you go from the optical to the near infrared, then out to beyond 2.5 microns, you wind up, your choices in what you use for transmissive materials change, and this means that you have to be rethinking what you're doing with the instrument, and in particular, when you're building an instrument that covers a very large band from 1 to 5 microns, say, your choices become very constrained. And this drives you often to using reflective optics, where you don't have a problem with material transmission, rather than using transmissive optics. But this is a factor that comes up. So you have then the detectors, the atmosphere, and the materials, and the background, all driving what defines different bands in the infrared. And depending upon the context, one or another may be more decisive in deciding which particular part of this, how you're going to divide up the spectrum. But they're all important. Okay, so I'm going to talk a little bit about the state of the art of instruments today. And to start that, I want to just get some definitions. People are a little bit fast and loose with this. We tend to not distinguish between resolving power and resolution, but there's an important difference. Resolving power is the ratio of the wavelength to the resolution. So the resolution might be measured in angstroms or nanometers or fractions thereof, but the resolving power is a dimensionless number that's the ratio of the wavelength you're at to the resolution. And the other thing that we sometimes use is the velocity resolution. So this comes out of radio astronomy, where we always talk about our resolution in velocity terms or in frequency. So it can get very confusing, but all it takes is knowing what the speed of light is, and you can get from one to the other. The coverage, we tend to give how much coverage you have in nanometers or microns or angstroms, so in wavelength units. An important handy number to remember is that both the H and the K windows are about 400 nanometers wide. This is about lambda over 5. So they're roughly, the width of the bands is about 20% of the wavelength. So that's a rough number to keep in mind when you're thinking about spectrographs. So the instruments that have been in use up to really the last few years, were all built when detectors were somewhat smaller, and that was driving the choices. And as we'll see later, when gratings were constraining things in an interesting way with the small detectors. So the generation of instruments from a decade and a half ago really are Seashell at the IRTF, Phoenix at Kitt Peak, and then later at Gemini, and CryRes on the VLT. And these instruments were high-resolution instruments with resolving powers between 50 and 100,000 in the infrared, but they had very small spectral grasps. So Seashell only covered 1/200th of the wavelength, and CryRes, which had the most coverage of these, covered about 1/70th of the wavelength with gaps in the coverage. Because the coverage was small, this means when you want to observe different lines or different parts of the spectrum, you have to rearrange something. So part of this can be done just by having filters that sort through different orders. But since you don't even cover an individual order with the instruments, you have to start moving things around. So you start having to move your gratings around, choosing different cross-disperser gratings, if you have a cross-disperser, moving your main grating, moving filters. And so the instruments tend to have a lot of moving parts. and in many cases, a lot of adjustments to how things are being done. So this is the optical diagram of CRIRES, which I won't go through. It had a reflective camera collimator set in it. Had a lot of pre-optics going into it, and the combination of these things lowered the efficiency significantly. And you'll notice, so this very faint line here is the border of the cryostat. So the instrument's cooled to 65 degrees, and there's actually a lot of reflections outside of that. It means that at the long wavelengths, there's additional emissivity, which adds to the noise of the instrument. But when you have many surfaces, that lowers your throughput, and it potentially adds to noise at the long wavelengths. Because of the limit in the grating sizes, we'll see in a minute, it's hard to get decent slit sizes at high resolution. This has largely been mitigated in a number of ways by using adaptive optics and by going to sites with good seeing. These instruments are also pretty big already, even on the 4 to 8 meter telescopes. And because they're big and have adjustments in them, they tend to be somewhat floppy. This is the new version of CRIRES Plus, which will appear on the BLT in the next couple of years. And it's the same instrument, but it has a much bigger detector in it, and that allowed them to insert a cross disperser. So instead of observing in a single order, they can observe in multiple orders at once with a somewhat shorter slit. And this increases the spectrographs with the instrument by about a factor of 10, and the instrument will now be able to fully cover the K-band in a single exposure. Unfortunately, because they're adding optics rather than taking optics out, the efficiency of the instrument will go down slightly when they do this. So it'll be a much more powerful instrument, but it will not be fundamentally more sensitive. This is another new generation instrument. This is iShell at the NASA IRTF. This instrument uses one of our immersion gratings, which I'll talk about later. It's a 1 to 5 micron high resolution spectrograph. It has a resolving power of about 70,000. It only covers the full spectral range in snippets, and the reason for that is that it's impossible to get the whole thing on a single detector at once, first of all, and then second of all, that they wanted to have the ability to have a very long slit, because the IRTF is about half of its time is devoted to planetary science, and in the planetary science world, the long slit, you want to have a slit that's long enough to cover Jupiter, and that when you put the long slit in, you can't cross disperse, and therefore you wind up with very small spectral coverage, even on the larger detectors. So this instrument is about 2 meters in size. So I want to go through the requirements for spectrographs and do a little bit of deliberation about where they come from, so you understand why we wind up with the instruments that we wind up with. And so I'll go through these, which I just tried to write this down, and there's some people here who know more about this than I do, but I wanted to write down what I thought the key requirements were and how they play out when we think about making spectrographs. So the resolving power, that is how finely you want to cut up the spectrum, is driven by a number of things. It's driven by science, and it's driven by technology. The diffraction limited resolution is given by the width of the collimated beam that you have in the instrument times the angle at which it's hitting the grating, divided by the wavelength. So this is essentially the number of waves of delay between the leading edge of the beam and the trailing edge of the beam. When you send the light onto the grating, the light hits one end of the grating first and then hits the other end of the grating last, and the number of waves of delay on the round trip gives you the diffraction limit of resolving power. Ultimately, though, you're limited by how long a grating you can get, and then by the need to let light into your system. So if you want diffraction limited resolving power, you have to have a diffraction limited slit, and that diffraction limited slit is going to wind up being very small on a large telescope. And so unless you have adaptive optics, you can't get anywhere close to that. when you're using natural seeing, you need to have the slit being significantly wider. And even with adaptive optics, you want it somewhat wider. But let's look at the signal-to-noise aspects of resolving power and how resolving power plays into your ability to detect lines astronomically. In doing that, let's fix the number of pixels per resolution element. So independent of what we decide the resolving power is going to be, let's say that each resolution element will have 3 pixels. So when we're at a low-resolution spectrograph, there'll be 3 pixels per resolution element. And in a high-resolution spectrograph, will be 3 pixels per resolution element. So we won't change that dimension. That's just basically how finely you're sampling the dispersion of light across your slit. And if we do that, we can write down a number of regimes and look at how your sensitivity to lines, or I also have the continuum up here, but in the other cases it's lines, how your sensitivity to lines varies with resolving power. So there are a number of regimes here. One is in the low signal-to-noise regime. That is at short wavelengths where your detector noise limit and where the background is low. And another is a high signal-to-noise regime. And then talking about short wavelengths, so that L's didn't turn into lambdas here, forgive that, short wavelengths and long wavelengths, where really what I mean is places where the background is low and places where the background is high. And so what we have here is in a series of different regimes where we're interested in our continuum sensitivity, in our sensitivity to unresolved lines, our sensitivity to resolved lines, and our sensitivity to emission lines that are unresolved, and ask how the line sensitivity varies with the resolving power. And so for the continuum, of course, the sensitivity gets worse. As you make the band that you're looking at narrower and narrower, you collect less light. When you go to unresolved lines, though, your line sensitivity is for short wavelengths where the background is low, your line sensitivity is independent of resolving power, and that's because the noise which is coming from your detector stays the same, and as you make the bands narrower, the lines get deeper, but you have fewer photons altogether. And so here's the whole list, and let's just concentrate on which regimes matter. In the high signal-to-noise regime, which is where you want to make precision measurements of characteristics, there your sensitivity improves as the square root of R. So this is because your noise is going up because your noise is going down because you're collecting fewer photons in the interval, and your ratio of signal to noise is going up at the same time. So you do better. Okay, so let me just say something about spectral coverage. And the first thing is like which wavelengths we want to cover. So we saw in the transmission slide that we have these bands that we want to cover. So we don't really want to cover in between the bands. And then really there are 3 regimes. There's the short wavelength infrared. That is wavelengths that are below 2.5 microns, where you're not dominated by thermal noise. What I would call the thermal infrared, which includes everything beyond that, but in particular here, I'm thinking in the L and M bands. And then we traditionally talk about the mid-infrared. So this is a region where you're totally dominated by thermal noise, where you wind up with a different set of detectors. And so this is essentially the 10 micron window and the 20 micron window. The 10 micron window is very transparent from most ground by sights over most of it, except at the longer wavelength N. But at 20 microns becomes very problematic. 20 microns is very chopped up by water, and you really need to be at a very dry site in order to work there effectively. And so we don't plan to have instruments that work at 20 microns, at least right now. When you design for this range, there are a lot of considerations you have to take into effect for optimizing your instrument that are a bit different than what you have in the short wavelength range. And so as we go with GMTNIRS to 3.5 and 5 microns, that drives a lot of our design considerations. And then in terms of spectral coverage, there really are three regimes again. One is just enough to cover the line of interest. And the early spectrographs, that's what they did. You wanted to look at a sodium line, you tuned up your instrument to look at the sodium line, and that's what you looked at. Then maybe large enough to cover a group of lines of interest. In the infrared, there's a lot of molecular bands, and so if you want to look at the CO band, you need a few hundred angstroms of coverage, and so you have to have that much to do it. And the other is if you want to cover, a whole spectral window, so the J window or the H window or the K window in a single exposure, and then you need to have 400 nanometers of coverage all at once. What we've discovered, we've built an instrument now that covers all of the H band and all of the K band in a single exposure, and what we discovered is it fundamentally changes the way you do science with the instrument. In the past, in the infrared, what people did was say, I want to look at bracket gamma in T-Tauri stars. And so they would pick a sample of T-Tauri stars, and they'd go look at bracket gamma lines in 50 stars. And someone else would say, I'm going to search for CO emission from the disks of young stars. And so they would go and they would look at the CO delta V equals 2 band region in the K band and look at 50 stars, maybe even the same 50 stars. And then someone else would say, I'm interested in magnetic fields. And so I'm going to look at the titanium lines. And so they would go and they would again observe the same 50 stars. What we find is as we have this more comprehensive grasp, as we're able to look across the whole spectrum at once, we're designing our studies differently, which is we're getting together different people with different science objectives and trying to decide on a signal to noise that we want, a sample, and a cadence, and then going out and making larger surveys and then pulling the data apart to use for the different astronomical purposes. So this is driving us in a somewhat different direction sociologically to how we organize the observations that we're doing from the traditional way that infrared astronomers have done it. And particularly on large telescopes, this is going to become an issue. With GMTNIRS, which observes the entire band from 1 to 5.5 microns at once, this will become even more a dominant mode where instead of individual people wanting to look across samples for particular things, we'll try to organize surveys that allow us to look, even though we're looking at one object at a time, we're collecting so much information on each object with this enormous spectral grasp that will design surveys that can then be used for multiple purposes and allow us to try to extract different types of information all at the same time. So we're figuring that as we go to large spectral coverage, that will actually change the way we do science. Okay, the detector. Well, the detector has a lot of requirements on it. One of them is many of which we don't have control over. We just have to beg and plead with the manufacturers. One of them is quantum efficiency. So the quantum efficiency is the fraction of the photons incident on the detector that turn into electrons that you can collect as signal. You want that as high as possible. For the detectors we use now, both CCDs and infrared detectors, this number is getting close to ideal. It's on the order of 0.8 or 0.9 in some cases. And you can't obviously do much better than that. When you pull the signal out of the detector, there's intrinsic fluctuations in the capacitor that the signal was taken on, and then in the amplifiers that bring the signal out. And this manifests itself as read noise. And the requirement is that the read noise be below any reasonable background. So at the longer wavelengths, the requirements for read noise are much less stringent than they are at the shorter wavelengths. And when you're looking for low signal to noise things, then you want the read noise as low as possible. I will mention that much of the science that gets done in the near infrared, in particular on stars, is done in a high signal to noise because you need to be able to look at faint lines. And in that case, the photon noise from the object itself dominates. And so it gives you a little bit of a break on the read noise also. You don't have to have absolutely perfect read noise to make things go. Yeah, I didn't set my timer when I started, so. Okay, the dark current, again, the detector generates its own signal a little bit, and the dark currents need to be below the reasonable background. So when you have when you're working in L and M, you can tolerate, again, more dark current than you can at JH and K. You get rid of dark current by cooling the detectors down more up to a point. And then the other thing is that the dark current builds up signal over time. So if you're observing for, say, 600 seconds, you want the square root of the number of electrons you generate from this dark current to be below the read noise of the detector. That way it doesn't have a strong effect. You want the wavelength sensitivity of the detectors to be as long as necessary, but not longer. What I mean by that is you can buy detectors that are sensitive out to some wavelength cutoff, say at 1.8 microns or 2.5 microns or 5 microns. You don't want to use a 5 micron detector in an instrument you're only going to use to 1.8 microns. Why not? Because it's right. You're sensitive to the thermal radiation from the outside world, and then also, which you'll then have to filter out, or from the ambient light inside the instrument. Again, even the instrument's cool, it's still going to be radiating inside. So if you have a long wavelength sensitivity, you'd have to cool the instrument that much more. So in the ideal case, you want your detector to cut off just beyond where the longest wave photon is that you actually want to look at. You want the readout speed of your detector system to be reasonably fast. And the reason is that because the detector noise is not perfect, we tend to read these detectors out many times in order to lower the amount of noise by averaging over the reads. And if the detector moves slowly, you actually lose time doing the readouts. Also, at the long wavelengths, the wells fill up pretty quickly because of all that background. And so you can't expose for very long. And if it takes a long time to read out the detector, you waste a lot of time that way. So they need to be able to move. Size, big. As big as we can get them, basically. Pixel pitch, that is how big the actual pixels are. People disagree about exactly what the best size is. But as we'll see, it becomes disadvantageous if they get too small at long wavelengths. Other issues are in the imperfection of detectors. We tend to think of detectors as perfect, but of course detectors aren't perfect. And two of the things that are most annoying are memory. That is, when you look at a bright object and then you go and look at a faint object, that you haven't quite cleaned off all of the signal from the bright object that was there in the past. That's really annoying when that happens. Also when there's a bright object in one pixel, and then you see some of the signal from that in the adjacent pixels because of electronic bleeding from one to the other. So you want your detector to avoid that. You also want it to be linear. That is, when you observe twice as long, you get twice as much signal. And that's fundamentally important. It turns out that even if it's not perfect, you can calibrate it out. You just have to know that it's repeatable and that you can get the same slight deviation from linearity each time. The well depth is important as well. The detectors essentially have, each detector in an infrared array essentially has a capacitor on which it stores the charge that's generated by the detector element itself. And this capacitor has a limited size. And so when that gets full, you stop getting any signal. The detector is no longer linear because you've saturated the detector. And so, on the other hand, if you make those capacitors bigger, the actual voltage that you see is smaller, and then the read noise gets bigger. So it's a bit of a balancing act. And the answer is they have to be big enough to allow high signal to noise per exposure. So let's just give an example. If your well depth is 10,000, then square root of 10,000 is 100. So you can get up to 100 to 1 signal to noise on the photon noise at that point. You don't want the detector well depths to be too small. The internal background is another issue. You have to cool the instrument down, otherwise the radiation from the ambient light inside the instrument will destroy your signal. And so this internal background is really a question of how cold you want your optics to be. And there's a pretty simple rule of thumb, which is that it has to be that the temperature has to be such that the background is less than the dark current plus the external background at the shortest wavelength you observe within a given channel. So this seems kind of odd. The thermal background outside is small. Why did I say it this way? This is a tricky question. It's the reason is this. If you have a detector that reaches out to some long wavelength, then it will see the radiation out to that wavelength inside the instrument. And so at the shortest wavelength, you have the least amount of light coming in from outside, and you want that light to dominate. And so in order to have it dominate, you have to drive the temperature of the instrument down to the point where the internal light generates fewer photons than the external light, even at that short wavelength. So that's just a decision about how cold you have to make your instrument. Then there's also a background that comes from outside, of course. That comes from the sky. It comes from your mirrors, because although the mirrors are reflecting, they do absorb a little bit, which means they emit a little bit. And so you have to have a number of factors to meet here. One is that you have to have something that blocks the light that's not light you need. So you don't want to see anything except the reflective surfaces of your mirror. So you generally form an image of your mirror inside the system and put cold material where there's no mirror. And that allows you to minimize the amount of background you get from the outside. On the GMT, with our instrument, where it sits on the instrument, this image of the mirror will rotate. And so inside the instrument, we have to have a little blocker that rotates along with it so that it blocks the right part of the image. That's one of the few moving parts we have in the instrument. And then the other thing is the question for background of adaptive optics. So Matthew alluded to this the other day. When you have an adaptive optics system, we'll see in a little bit that it makes a huge difference in terms of the size of the slit you want, but it also affects the background noise. When you have an adaptive optics system, you inevitably have more surfaces. Even when you have an adaptive secondary, we wind up effectively with a bit more surface that's emitting light and then generating noise. And what you win when you do that, though, is because you can now make your slit narrower, the A omega that you're looking at is smaller. So the A, in this case, is the area of the telescope. And the omega is the solid angle in the sky of a resolution element, or your slit width times the length over which you're looking along your slit, which is essentially the size of the adaptive optics seeing. Now, when you have a small telescope, this A omega is close to 1, it's close to the diffraction limit. As you make your telescope larger, the seeing disk stays the same size, but your diffraction limit gets smaller. And so A is getting bigger, but because you need to get the whole seeing disk through your instrument with a natural seeing instrument, omega doesn't get any smaller. So the background on a pixel goes up. If you use adaptive optics, you're allowed to make this number stay small because the diffraction limited size of an image gets smaller as A gets bigger directly. So this stays constant. And so this will stay constant as the telescope gets bigger in the case of adaptive optics, while A is getting bigger and allowing you to put more signal on. If you have to use natural seeing, then your slit keeps getting wider, and so omega keeps getting bigger, and while A gets bigger. So you don't get rid of background. And so what this means in practice is, on small telescopes, adaptive optics doesn't win you any sensitivity. The break-even point is at about an 8-meter telescope. So if you look at adaptive optics spectrographs with slightly lower efficiency, due to the Strel not being perfect, and a few more surfaces improving making the emissivity worse, against the smaller beam making the area that you're covering smaller, the solid angle you're covering smaller, you about break even. When you go to the 20-meter class telescopes, you win big. So the 20-meter telescopes are the first ones where infrared spectrographs really win by having adaptive optics. And that's one of the things that drove our decision to build our instrument as an adaptive optics instrument. Okay, well, throughput, this is a self-evident one. The more throughput you have, the better, because you get more light. But not all bands are equal. In the near-infrared, where you're going to be limited by the noise from the source, the more throughput you have, the faster you win quite quickly. You're not adding to the background. When you go to 3.5 and 5 microns, the background's going up as the throughput goes up also, and so you only win more slow. You only lose more slowly as the throughput goes down. What this says, you still want the best throughput you could get, but if you have a trade to make, what you do is you try to maximize the throughput at the short wavelengths at the expense of the long wavelengths. And you'll see in the design of the instruments that we propagate, once we're in the cold space, where emissivity is not a problem, we propagate the light through the instrument, picking off light for the short wavelengths first and then for the long wavelengths last. And that's because we lose less signal to noise if we do it in that order than if we do it in the other order. So you have to kind of think about these things as you go along. Okay, so sampling, so that is how many pixels you're going to use per resolution element. It's a combination of the real estate you have and a noise question. So real estate is the more you oversample, the shorter your slit's going to have to be if you're cross dispersing, or the less bandwidth you can cover. Another disadvantage of large numbers of pixels is then when you look at a resolution element, you're going to have to average pixels together, and there's going to be more noise because you're putting less light on each pixel. Those two things are outweighed by the fact that as you shrink the number of pixels down, if you don't sample the slit enough, you don't get a good spectral PSF. You don't get a good spectral response function, and so you worsen the resolution of your instrument. And that, again, is painful, both because you get less information and because you, well, the main reason is you get less information when you do it. So it turns out that the sweet spot lies between about 2.5 and 4 pixels per slit width, per resolution element. That's just rough rule of thumb, and you'll see that most spectrographs are in about that range, except in the era when the detectors were very, very small. The slit length needs to be long enough that you can move the object back and forth across the slit, so we can take out all those darn OH lines that show up. So how long the slit is depends on how big your source is, and that will depend on whether you're using natural seeing or adaptive optics. So with an adaptive optics instrument on the GMT, a slit of an arc second or so is fine. Typically with natural seeing, you'll need a slit of at least 5 arc seconds to make this work. The one place where you want the slits longer is when there's a science reason to do it. So planetary astronomy or work in the interstellar medium, and I'll be talking about a little bit of interstellar work tomorrow, those require us to have longer slits. Oh, thank you. Okay. I don't think I'll skip this one. So another thing is spectral stability. So Andy talked about doing work on precision radial velocities, and that, of course, requires enormous stability. And you want to have the intrinsic stability of the instrument be as good as possible, and then you want to have calibration standards that keep it even more stable than that. So you really want to have both. But in addition to that, there's stability of another sort. You want stability in the gains of your instrument and things like that, because they are essentially what limit your ultimate signal to noise that you can get. So in particular for people who are observing low metallicity objects with very, very, very weak lines, you need to be able to reach very high signal to noise. So the instrument has to not only be linear, but it also has to be stable enough that in long integrations you're able to see these very faint lines. And we'll see some examples of that also when we start talking about the astronomy. Okay, so let me talk a little bit about GMTNIRS and tell you something about how it works. So GMTNIRS is designed to essentially look at all the infrared that's of interest from the GMT site at once at very high resolution. So it covers a band from 1.07 microns out to 5.3 microns in a single exposure. And it does it at a resolving power of 65,000 when you're below 2.5 microns and about 85,000 when you're above 2.9 microns. So the J band actually goes a little below the 1.07 microns. So why do we stop at 1.07 microns? If you remember the first slide I showed, you'll know the answer. No, it's not the sensitivity of the detector. It's because the detectors are these mercuride telluride detectors are sensitive down to about 800 nanometers. It's the transmission of silicon. We use silicon immersion gratings in the instruments, and they don't start transmitting until about 1.07 microns, and they only do that when they're cold. So this allows you to get to the helium-10-830 line, for example, but just barely. And it's a real physical limit that we can't get below. This is really where the atmosphere stops transmitting, and so we're stuck with this limit too. So we divide the spectrum up into 5 bands covering the 5 windows, and then treat each one separately, having a separate optimized spectrograph for the instrument. So we have a 65 milliarc second slit. The GMT, the diffraction limit, is about 8 milliarc seconds at a micron. And so 65 milliarc seconds is about 1.5 lambda over d at 5 microns. And so that allows us to get a reasonable amount of signal through at the longest wavelength we work. The instrument has no moving parts after the slit. This allows it to be very stable over time. By using this one spectrograph per channel, we're able to tune all of the materials to get high throughput. It's got a K-band slit viewing camera built into it. This allows us to find and position ourselves in complex spaces on objects that are not visible. That's turned out to be very handy in our current instrument. And then because it has a fixed format, because there's no moving parts, we can have a pipeline that produces near science quality data right out of the box. And this is critical when you've got so much data coming in to be able to look at it in a more close to final form pretty quickly. So this is a picture of the instrument on the rotating instrument platform. So the big instruments are down here, and we're up here. The tertiary mirror sits here and can be turned to point at the different instruments depending upon what you're doing. So you can only look at one of these near-infrared instruments at a time. This is about 2 meters from here to here. So it's big on my scale, but it's small for an instrument on a 20-meter telescope. And it then, because it rotates around on this rotating platform and the telescope tips, it can present itself to sky at any angle. So it has to be ready for different angles. This is always a bit of a trick with infrared instruments. So here's an exploded view of the instrument. The top and the bottom come off. Everything's mounted to the middle, and this is the radiation shield. So the inside of the cryostat radiates, of course, at 300 degrees, and then you have a highly reflective shield around the instrument that reflects most of that back, and you actively cool this shield to keep the inside of the instrument from radiating very much, and so your detectors don't see a lot of radiation. And then this whole thing is mounted to the outside by this series of straps that don't conduct much heat and allow you to keep this part cool without a huge amount of cooling power. The sensitivity shown here, this is an old chart, so it's got the wrong resolving powers on it, but it's approximately right. Shows you sensitivity is a function of wavelength for the different bands. So this is M, L, and then K, H, J here. And if you look at signal noise of 100, this is a fairly conservative estimate. So 600-second exposures, which is about the longest we like to use, for an image size equal to the slit size. So that's actually an underestimate because the image is typically going to be smaller across the slit, so there'll be fewer pixels involved. And not calculated at the peak of the blaze of each order, but at an average place. And the way I like to look at this is sort of a science look, which is in JH and K, GMTNIRS can take a signal to noise of 100 spectrum at R of 50,000 of basically anything in the 2-mass catalog in under an hour. So whatever you find in the 2-mass catalog, you say, I want that, and in less than an hour you can have a high signal to noise spectrum of it. So that's a tremendous capability that allows us to look at basically anything in the galaxy and do something really good with it. So this is a diagram showing the light path. Let's go through this very briefly. The 4 optics. This is actually for use on a different telescope, and this part here will be replaced by that rotating pupil stop I said. Here's where the slit is, and then the way the instrument works is we divide the light up between between the different wavelengths and essentially have a separate spectrograph for each wavelength. So here, for example, is the spectrograph for the K band. The light comes to it through a series of dichroics, and then the light goes to a diffraction grating here, which is a silicon immersion grating. I'll talk about those a little later. And then goes from there directly through a volume phase holographic grating that sorts the orders, and then into a camera and into the detector. So it's got very few parts in it, and the parts are all the coatings and everything are narrowband coatings that are optimized for this particular set of wavelengths. Then the L and M make it. I didn't put this up first. I thought I'd scare you with it, but the L and M spectrographs are each back here. So J, H, K, and then L and M spectrographs here. And L and M, you can't use volume phase holographic gratings, so they have reflection gratings for the cross dispersers. But each spectrograph is quite small. You can see this is 0.5 meter is the bar on the bottom, and so the spectrographs are actually quite small, and it's just that we have to have 6 of them to get all the signal that we want to get. And the reason they can be so small is because we're using the adaptive optics to bring the light in. So I want to spend part of the rest of my time going through a simple way to design a spectrograph. So this is a way that I do my preliminary thinking about spectrographs, which does not involve using the grading equation. So it uses a few very simple rules. And this allows you to design in your head a small spectrograph. So the diffraction limit, limited resolving power is equal to the number of grooves, n, times the order that you're in for the spectrograph. So that's one rule. The number of diffraction limited resolution elements per order equals the number of grooves in your grating. The diffraction limited spot size at the focal plane is just the F ratio times lambda. So that square is a time sign. I don't know why it turned into that. And then another thing is that the diffraction limited, unless you mess with your optics in a totally weird way, the diffraction limited spatial and spectral spot sizes are the same. So when you disperse the light, the diffraction along this dispersion direction and across the dispersion direction, a spectral resolution element and a spatial resolution element have the same size. The real resolving power is just this diffraction limited resolving power times the ratio of the diffraction limited size, so lambda over d, and the size of your slit. So putting all these things in, it's just n times m times lambda over d divided by the slit size. The middle part of this last equation is dimensionless. On the right, you have to put the slit size in radians to make this work. So if you just take these things, you can design a spectrograph. So I put together an example just to show you. Let's just imagine we need to design a spectrograph that can cover the entire K-band, so 2 to 2.5 microns, in a single exposure at R of 50,000 for use on the GMT. So we need to start somewhere, and the place to start is with the detectors. When you go to the store now, what you can buy is a 2048 by 2048 detector with 18 micron pixels from Teledyne. Now, you'll have export problems if you want to bring them here, but you can manage it with a little bit of extra money and a little bit of extra time. Anything else you want, you're going to have to wait a long time for and pay a lot of money for, because custom products like this are kind of what NASA does, not what we do. And let's just say we need a slit of about 70 milliarc seconds. This is about 4 lambda over d. And on the GMT, this will protect us from a couple of possible gotchas. One is that if the mirrors don't phase up perfectly at the short wavelengths, then this will capture all the light from an individual mirror, and so we won't lose any efficiency even if the phasing is wandering around. It also allows us, when we look at fainter sources where it's hard to tilt guide, if there's some image wander, it'll still capture all the light coming through the slit. So using a bit bigger slit is helpful. And just as a reminder, this also, if we want to let light from longer wavelengths through the slit, it'll be good to have it that way. And let's also decide we want to use 4 pixels per slit width. Remember, I said that the optimal was somewhere between 2.5 and 4, and 4 will make calculating easy here. So the diffraction limit of the telescope's 18 milliarc seconds. If we need a slit of 70 milliarc seconds, that's 4 lambda over d. We're going to use 4 pixels per slit. That means that each pixel will correspond about to the spatial diffraction limit. So the 4 lambda over d slit is 4 times the resolution we want, and it's four times bigger than the diffraction limited size. And so we have to have a diffraction limited resolving power of 200,000 to get this 50,000. So our grating has to produce this to get that with the slit we're using. The resolution per pixel is about 200,000 because there's 4 pixels per slit, and the ratio of these is 4. So the two together then are means we have 1 diffraction limit per each pixel. And so the diffraction limited spatial element is also going to be 18 milliarc seconds. We're going to use 18 milliarc seconds per pixel. Okay, so when you make a cross-dispersed instrument, the order lengths are not the same at all wavelengths. And so you can't use if we're talking about the middle of the band, you can't use the whole detector. You have to use a little bit less. So with our 2048 detector, let's say we use 80% of it, or 1,600 pixels. So because each pixel is the size of a diffraction limited resolution element, then remember that the number of grooves has to equal the number of diffraction limited resolution elements in an order. So if you want to get one order, we want to get the full order on the detector, our grating has to have 1,600 grooves. That will make the middle order, the 2.2 micron order, free spectral range, cover 1,600 pixels. So we can ask ourselves then, how long does this grating have to be? To get a resolving power of 200,000, the grating has to be, it has to be 200,000 waves long in the direction of propagation. So this equation is just simple geometry. It has to be 200,000 wavelengths long in the direction of propagation. So this sine delta is then the angle of incidence on the grating. And so when you put in the numbers, the wavelength in meters is 2.2 microns is 2.2 by 10 to the minus 4. What did I do here? Oh, sorry. Here's the one in centimeters. I'm doing this in centimeters. So this is in centimeters, 2.2 by 10 to the minus 4. The resolving power is 200,000, and then sine delta, the best you can get is about 0.9, so this number is 1.8. When you put those all in, your grating has to be 24 centimeters long. Well, that's not too bad. 24 centimeters is a decent-sized grating, but it's not, you can go to the store and buy one. But we're only allowed to have 1,600 grooves. If we have more grooves, then the orders are too long, and they stretch off the edges of our detector. So 1,600 grooves divided into this 24 centimeters means that each groove is 160 microns. So that's a groove density of 6 grooves per millimeter. So Andy, can I go to the store and buy a 6 groove per millimeter grating? He's nodding his head no. There's no way, we can't even get close to making something this coarse. Most gratings are made, the originals are made by scratching a diamond through soft, sintered aluminum material. So you have to dig the diamond into the material to do it. And the coarser the grating, the deeper you have to dig. And you simply can't dig that deep into metal, and so you cannot do this. So this can't be done conventionally. What's the camera F number have to be? Well, F lambda, which is what gives you the size of the diffraction beam, has to equal the size of a pixel, we said. And so F lambda has to equal 18, lambda is 2.2, so we need F8. That's a very slow camera. That's easy to do. So that at least is easy. So this is impossible, this is easy. Okay, now, the only question left, let's assume we can make the impossible possible. The only question left is cross dispersion. So the total band is about 0.22, and so that means we need, at our resolving power of 50,000, we need 0.22 times 50,000 resolution elements. That's 11,000. So our central order has 400 elements in it. It's 1,600 diffraction limited resolution elements long. We have 4 diffraction limited elements per slit width. So we have 400 resolution elements. So we have 400 elements, we need 11,000. That means we need 28 orders. So if we can spread these in the vertical direction on our array over 2,000 pixels, that means we have 71 pixels per order. Our pixels are 18 milliarc seconds, times 71 is 1.3 arc seconds. So the average spacing between orders can be 1.3 arc seconds. We need to leave some space between the orders, so the slit length will be closer to 1 arc second. It's a good thing this is an AO instrument, because if not, that would be a very short slit, and that wouldn't work very well for us. So by just going from those basic principles, we're able to figure out how fast our camera has to be and what the grating properties are, and everything else is just mechanics from there with a little bit of optics. Okay, so I have a few minutes left. I want to just quickly go through something about the secret sauce here, which are the immersion gratings. Sitting over lunch many years ago, we had the great idea that if you want to work in the infrared and make diffraction gratings bigger without making them physically bigger, if you shine the light into a dielectric, the wavelength shrinks by the refractive index of the dielectric. And so it gets shorter. So you get more interference, more waves of interference between the leading edge of the beam and the trailing edge of the beam for a given length size. And if you did this in silicon using etching techniques, you could make very coarse grooves, which will solve our other problem. So you can write down the grating equations, and I'm not going to go through these here. This is the basic grating equation here. And the one difference is you put in this n for the refractive index, because, so you leave the vacuum wavelength in, and you put in the refractive index, and otherwise the grating equations look the same. So the resolving power you get goes up by n, the dispersion goes up by n, and away you go. So this was great. This was 1992, it was a long time ago, had this great idea. So we said, wow, we've discovered something very fundamental, let's go patent it. Well, sigh. Somebody had already patented it in 1984, and so that was not going to work. And here's the patent. They weren't making them the same way we were, but they had written in all these weasel words that said they would sue us if we tried to patent it. But then we discovered in 1954, somebody had written a paper in Nature where they described exactly the same thing. And so the patent probably wasn't valid anyway. And then one of my students who had been working on the grating project, when she was writing her thesis, said, well, you know, I think this is a little older than this. And so we dug around, and we went to the rare books library at UT, and we found this, which is Josef Fraunhofer in 1823, so almost 200 years ago, had dipped diffraction gratings in different substances, in water and in turpentine and in linseed oil, and measured the diffraction power of the gratings, and he'd written down those exact same equations we had there. This paper contains those equations. So he'd already figured this out. He couldn't make the ones we can make, but he figured it out. We do it by specially preparing silicon. We take a boule of silicon and we slice at an angle a disc out of that silicon. So this disc here is about 30 millimeters thick. And then we polish it very, very carefully, very flat with a special chemical technique. And then we etch grooves. And silicon has a bunch of intersecting crystal planes. And if you dip it in KOH, it etches across a potassium hydroxide. It etches across the 100 plane of silicon about 100 times faster than across the 111 plane. So if you put a set of stripes down on your substrate, then the silicon will etch away until it reaches these 111 planes and produce a groove with an opening angle of 70.5 degrees. So from the outside, the grooves would shadow each other, but from the inside, that doesn't happen. So if you're shining from the inside, that angle's not a problem. So we go through a series of steps, and this is very much the way manufacturing is done for microelectronics, or was done 25 or 30 years ago. We use what's called contact lithography for most of it. We do some electron beam lithography to pattern a series of stripes, and then we sequentially remove different layers, trying very carefully to keep the precision exactly right of where the stripes go. They have to be positioned to about 20 nanometers over about 20 centimeters. And then we dip it in KOH, and it etches away to make these triangles. Then we cut a face off of it and anti-reflection coat that face, and then the light comes in here, hits the grating, and comes back out. This part's not optically active. We leave it there for mechanical stability purposes. So this grating is about 90 millimeters long, and the opening window is about 30 millimeters on a side. We test them in a variety of ways, and this is perhaps the most important. This is efficiency versus wavelength, measure for the grating that's in our IGRINS instrument. And this line is at 0.75. That's about the highest efficiency you can get with an optical grating you can buy. And we're getting that even counting going through the window at the front of the thing and coming back out again. So this is just some manufacturing things, testing of our gratings from the front surface using interferometry and making high dynamic range spectra of laser light. And we've made gratings as fine as coarse as 5 lines per millimeter. And the grating we needed in our example was 6 lines per millimeter. But when you come from the inside, the wavelength shrinks. So actually, we would have only needed a grating of that was 18 lines per millimeter in that case. So we can make gratings way coarser than are needed for examples like I gave you. So we do some of this work in a clean room and produce these things. This is another technique we use, writing the gratings with electron beams rather than using masks to make the contacts. More testing. And then we've developed, as we worked on this over the last 2 decades, we developed kind of a measure of how hard it is to do, and that depends on, it depends on how long the grating is, the width divided by the width of the slit, and it also depends on the wavelength that you're working at and the angle, that angle delta. So we built some some transmission gratings for the forecast instrument on SOFIA that worked at 30 microns. Those were the first ones that were deployed, and those we called degree of difficulty 1. So just like the divers in the Olympics, you know, if they do a triple somersault with a half twist, that has degree of difficulty X, and if they do a quadruple somersault with a double twist, it's higher, it's more difficult. So we got more difficult with time. We made great grisms for the JWST. They were about degree of difficulty 10. The grating in IGRINS is about 100. The ones for GMTNIRS, the short wavelength gratings, are degree of difficulty 250. And so that's one of the reasons why we've been working the last 4 years to build those. They're much harder to build. So this is the spectrum from iShell, and it's interesting because it shows that you can reach all the way down to the 10830 line, which would be here in this spectrum. So the transparency of the silicon, this wasn't well known. You have to use very high resistivity silicon to make this work. And then we built things for a lot of different purposes at this point on Airborne Observatory and on IGRIDS. So let me just skip a little of this to. So this is IGRINS. This is the instrument we built as a prototype for GMTNIRS. There's the immersion grating. So it doesn't take up very much of the space within the instrument. It's just, but it allows the rest of the instrument to get small too. So we work with 25 millimeter beams in this instrument. Here's a diagram of the optics of this instrument. It covers 1.4 to 2.5 microns. It's a collaboration with Kasi, who's another GMT partner. It has a resolving power of 45,000. It's been on the 2.7 meter telescope at McDonald, on the 4.3 meter Discovery Channel telescope of Lowell Observatory, and it's on its way now to Gemini South, where it will be all of this spring. And it has then at Gemini about a 5 arcsecond long slit that's about 4/10 of an arcsecond wide. So it's a pretty narrow slit there, but there's nothing I can do about it. And anyway, the light is collimated, dispersed by the immersion grating, and then split between the H and K bands. And then we have, it's folded, and then there's a volume phase holographic grating here, which is very efficient, that then sends the light into a camera, and it hits each detector. Here the instrument is on the 2.7 meter together with the Korea UT and McDonald Observatory team installing it. The instrument's only about a meter across, so it's a very compact instrument. Here it is on the back of the telescope there. Oh, and this instrument now has no moving parts at all. So it has no internal moving parts, and we took away the calibrator box and just used night sky OH lines and absorption lines for calibration and a white spot on the ceiling, so it actually has no moving parts anywhere. Here, just as an example, here's one order of from 2014 of IGRINs. This is the spectral coverage of the Phoenix spectrograph shown on that one order. So the Phoenix was the workhorse instrument at the 4 meter at Kitt Peak for a long time, and spent a long time until actually just last year. This is the last time it appeared at Gemini South. It covers this much spectrum, typically at RF 50,000 with the same slit size we use. And this is the total coverage of IGRINs. There's 43 orders. Remembering that one only covered a fraction of an order. So this is the whole this is the whole H and K band now. This is the way the atmosphere looks when you look. So some of these orders are not so great, but most of them are pretty spectacular. So that's what we have, and we're looking forward to putting this instrument together. And I'll be talking over the next couple times about the science we'll be doing with GMTNIRS. So I'd be happy to take some questions.
Questions? So let me start. So there's a lot of breakthroughs, it seems, and lots of unique things in the design. So does GMTNIRS have any competitors?
Well, it depends on, so the answer is, if somebody wanted to do what we want to do, no. So I didn't put that slide in, but because someone complained yesterday about comparing to old instruments. I don't know who was making that complaint up here in the front. It was dark at the time.
Alberto, he's not here.
But so we did a comparison against CryRes, and of course CryRes is now being upgraded. But against CryRes, if you wanted to look at the whole spectrum at R of 100 you wanted to look at the whole spectrum at high resolution at once, to 100 to 1 signal to noise, then GMTNIRS would be 10,000 times faster, right? Because you'd need to take 200 separate exposures with CryRes to get what we get, and then with the telescope advantage and our throughput advantage, we'd get that far. If you want to look at a given line, other instruments will be competitive. Nobody's building this high resolution instrument yet for one of the big telescopes, right? At these wavelengths. METIS will come down into the 3.5 micron range, so 3.5 and 5 microns, but it's designed with an IFU specifically to do planetary transits. So it's going to cover a small snippet of spectrum. So that particular mode of the instrument is focused on a very particular problem. This is a general purpose spectrograph. It's not going to do precision radial velocities. We might get to 10 or 15 meters a second if we're lucky, but it's going to be sensitive and it's going to cover everything. And so you'll see that there are advantages for certain types of things that you can do a lot of different science questions at once when you look at the same object. And then Andy and I were talking earlier today about, we've been looking into this possibility of being able to use being able to use his instrument, GCLEF, at the same time by an optical arrangement. So for things like planetary transits, where you need to sit around for a long time, we'd be able to look at the whole spectrum from 3,000 angstroms out to 5 microns in one go.
So you mean having a dichroic tertiary?
Yes.
So
Yes.
you can...
Yes, exactly. And so for many purposes, that's just overkill. But for certain things where they take a fair amount of time and you want all the different information at once, that could be very valuable. So the answer is, it depends on what you want to do. But if you want to look at a lot of stuff at once, if you want to look at a lot of spectrum at once, nothing will touch it.
Congratulations.
Well, one thing that you briefly mentioned and caught my attention very much, the K-band slit viewing camera.
Right.
And so can you expand a bit on the guiding for the instrument?
Right.
And if it's related, if there is a guiding system for the telescope?
So it's an adaptive optic system, and the usual mode. So for most of the science, you're in this spot where you want to have high signal to noise. So the objects are, when you're working at R of 65,000, it means the objects in continuum are quite bright. And so we'll use laser guide star AO to correct the wavefront. But because of the ambiguity of up and down, the laser guide stars do not take the first order tip and tilt out of the spectrum. So you have to have an object that does that. So we're actually going to steal about 10% of the H-band light and tip and tilt on the objects we're looking at. So in most cases, we'll be able to do that, because if you're looking at stars, it's the same object. There are a few cases where we're wanting to look at the, something that's slightly offset, but there'll be a limited field that will allow you to do very small offsets. When you're wanting to do low signal to noise things, so for example, one thing which I'm not going to talk about, but which you could do with this instrument, is you have 20,000, 30,000 spectral resolution elements in the near infrared. You could imagine wanting to measure the radial velocities of, K of 19 objects, of, faint brown dwarfs or very distant dwarf stars or something like that. You can do that at signal noise of 2, right? Because you have all of this. You can't guide on that. So now you have to have some kind of optical guide, optical offset star in order to be able to do that. The K-band. The thinking about the K-band camera is there are many situations where you go in, and in particular star-forming regions where there's a lot of stuff going on, you want to know that you're on the right object when you're spending as much per night as we're spending. And so you really need to look at the field right then and there and say, it's really that one on the left. The other place where this happens is inevitably true. We're going to go into a binary system, thinking we're going to take a spectrum of both objects. It's going to turn out to be a triple. And so we then have to think, well, where do we want to rotate the slit, and so on and so forth. So we're going to need guidance, not guiding, okay? And that's really what it's for. The guiding will be done by the tip-tilt system, mostly.
Thank you.
I have several questions. I will ask them offline. I will ask just 2 of them here. When you do a 600 second exposures, so you deter in space, and you also deter the 6 of them in wavelength?
No, we don't change the wavelength at all. So the whole format of the system is fixed. So you can't change the wavelength at all. So this is
I'm asking just because you said in the beginning you have to do that in order to get rid of the OH lines.
Oh, so we do that in space. So when we look at point sources, we put the point source near one end of the slit and we take an exposure, and then we put it near the other end of the slit and we take an exposure. We take we take A minus B, and that eliminates as long as there's not a lot of sensitivity variation along the slit, which there shouldn't be, that takes out the OH lines to a very high degree.
Okay.
What I'll show tomorrow, a lot of work we've done on interstellar medium sources, and there it's very painful because you switch off onto blank sky, and you essentially have to waste an exposure on blank sky, And then, even then, if there's any water vapor or something, the transparency will change, or the OH lines will fluctuate. You won't get rid of them perfectly, and you'll hate yourself for having spent that time. So it depends on the context, but usually we just move back and forth along the slit.
I see. The other thing is about iGrins, that it doesn't have adaptive optics, right?
That's correct.
Okay. So besides the adaptive optics, what other steps you're going to have to do between iGrins and GMTNIRS?
The main thing is that going to L and M, to the long wavelengths, we need bigger gratings. And the problem is that the tooling we have in place and a lot of the industrial tooling is very limited in terms of what size things you can make out of silicon. And so we've had to develop a whole lot of new infrastructure to build the larger gratings that we need for the L and M bands. That's been the dominant part of our efforts, is getting that taken care of. Beyond that, it's just that those instruments now have reflective cross dispersers, so there's somewhat different design. I mean, the short wavelength ones are basically parallel to iGrins, but it's not a huge difference.
And is there? Sorry, I'm already asking more. Is there? Is GMTNIRS started? Has GMTNIRS?
No, we've been in a phase where we've been developing the gratings because. Let me put it this way. Many people have started to make immersion gratings and failed, right? So a number of groups have attempted to do this and really not been competitive. We would place ourselves in the same category of competence. We're just more stubborn. And so our yields are low, and so it takes time. We weren't willing to engage the risk of building an entire instrument that depended on 5 immersion gratings without making the immersion gratings first. It was scary. When we started iGrins, we were about a year and a half in before we succeeded in making good enough immersion grating. That was a very nervous time for me, and I didn't want to go through that again. So we've been spending this time building those more difficult immersion gratings, and we're through several of them now. We're not quite finished. Before we actually started putting serious effort and serious money into the instrument, just because I wanted to retire that risk before we started.
Great, thank you.
You mentioned that you built one JWST grating.
Yes.
This is not immersion grating then?
No, this is it's a silicon grating, but they're transmission gratings.
Okay.
So the NIRCam instrument has 4 of our gratings in them. They were originally going to be a backup system for aligning the segments. So the segments are aligned in the optical, but the capture range of the optical system is very small. And they wanted to have a longer wavelength system to improve the capture range just in case. Mm-hmm. And as it turns out, they found another form of metrology that can do this a little better. They left the gratings in. They will give NIRCam a slitless spectroscopy capability. Mm-hmm. So you can do slitless spectroscopy of faint galaxies or whatever with NIRCam because these gratings are in there. They're because the background's still an issue when you work with even in space when you do slitless work. You have to choose exactly what you're doing, and typically you'll want to be near the peak of the blaze and with a moderate size filter, so your wavelength range is not going to cause a lot of confusion. But people are thinking of science programs, and there are science modes implemented that use the gratings.
Okay, thank you.
Any more questions?
If I understood well, you said iGrins is coming to Germany South, spring or north, hemisphere or south, say this year?
This year.
And for how long?
Well, sorry, it's northern spring. That's it's coming now. It's going to. It's. I'm in our spring. I'm sorry. This is geo-chauvinism here. It's arriving within the next few weeks, and it'll be on the telescope for about 3 months. So there should be some of this. What are those proposals called? The rapid. There's the opportunity. There's that rapid turnaround opportunity. There's a limited amount of time available for that, and I think they reserve some queue time for rapid turnaround proposals. So it'll be on. I think we commissioned the first week in April, and we'll be on until the middle of July.
Someone else? So I would encourage you, if you have any questions, any doubts, and you don't want to speak here in public, take the opportunity of the breaks. We plan this school with large breaks, so you approach the speakers. I'm sure they will all be very open to that. So, and ask your question and talk about your project. Okay, let's take advantage of having these very, very clever people among us for this week. So, thank you again. Coffee break now.